Good morning. We're on to lesson 7 notes where we're going to talk about exponential and logarithmic regression. So you already touched on exponential regression in the last unit. So it's basically the exact same process, but now we're going to do it with logarithms, and we're going to make sure we know the difference between an exponential and logarithmic regression. So I have posted as well the calculator keys again in this topic because there are a lot of things to push, and I tried to include it all in your notes so you can reference it as well. But please, again, don't hesitate to contact me if you're having trouble getting your calculator to do what you want for this. Okay, so we've already talked about regression. Basically, it means you've gone and you've done some research and you've collected data, and you have a bunch of different data points that you can plot. And now you want to come up with an approximate equation to represent those plotted points, kind of a line of best fit. This is called a regression equation, and it kind of approximates your data so you can make predictions and answer other questions. So first of all, we're going to look at which of the following scatter plots would be a best fit with a logarithmic equation. So knowing what you know about how a logarithmic equation would be graphed, we can look at these data points and see what they would represent. So this one, the first number 1, if you kind of draw a line of best fit, it looks like it's more or less kind of a straight line. This is an example of a linear regression. If I had those data points and I wanted to continue on with that pattern, I would use a linear regression in my calculator. Number 2 has a bit of a curve to it. It's kind of up high and it curves down. This is an exponential regression, but it's decay. Exponential decay. Remember, for exponential, usually we work with it going like this. That's exponential growth, but it can be the opposite way, which is decay, which is what that is showing there. Here, this one again has a bit of a curve, and again, some of this is guesswork. Some people might have seen that more linear, some might have seen it more exponential. It kind of depends on the information you're given. But I can see a definite curve here. This is exponential, but now this shows you exponential growth. Okay, to go back to your very first lesson on logarithmic functions, we talked briefly about how they look when you graph them. When you see this one here, you can see it's a curve like this. This is a logarithmic curve. It shoots up really, really fast and then it starts to level off. That's a classic logarithmic regression. Okay, so let's look at an example. Most of this is just figuring out how to use your calculator properly with it. So I'll work through one with you. Here's example 1. It says, during prolonged cold in northern latitudes, thick ice will grow on lakes. A particular lake in Ladysmith, Wisconsin, has its ice thickness measured every day after the temperature fell below 0. And here is my data in my table. Now, often in the questions, it'll give you a hint what kind of regression we want to do. So it says, find a logarithmic equation that best fits this data set. So we need to go into our calculator and figure out how to do that. So remember from last unit, we're going to list all these values in our list function. So this will be my list 1 and my list 2. So you're going to go into your calculator, and you're going to go in the stat button, and you're going to go to edit. And now you have your list 1 and list 2. You probably still have stuff in it from last time. Remember, you can go highlight the title and hit clear, enter, and it'll clear your whole list for you. Okay, so now we're going to start with our list 1 values. Always your x values go in list 1, your y values will go into list 2. So here I have a 6, 9, 14, 20, 27, 32, 55 in my list 1. Then I'm going to move over to list 2 and enter in those values. Make sure you enter them in carefully. If you make the mistake typing them in, it'll change your formula or your equation. Okay, so now that I have them all entered in, now we can actually do the regression. So we're going to go back into stat. You're going to move over to calc. And now you're going to go down to the one that says LN regression. This one here, number 9. Okay, Once you have that, again, your calculators might look different. If you have the newer version, it'll look just like mine. If you have the older version, it might just say calculate at that point. You need to, either way, you need to go and store the equation. This puts it into your graphing y equals window so that it graphs the exact accurate equation without any rounding. So if you have my calculator, it's going to look like this. You're going to go down to store. If you have the older calculator, don't push any buttons. You're just going to go straight into bars. And you're going to move over to y bars and then hit enter, enter. And it's going to store y1 for your graphic. And then you can go down to calculate. Okay, it tells you how to write out the equation here. So you can see what your a value is, and you can see what your b value is. So you just need to substitute it in, and it tells you exactly how to put it into the equation. For this one, we said round to nearest 10th. So my a value is going to be negative 4.5. So now I can write that out here. And then my b value is going to be 2.9 when I round it. And then I have log x. We use natural logarithms for our graphs. It's just a certain form of logarithm. So that's why it doesn't say log, it says ln instead of logarithm. So that's my equation. It also says determine the value of r squared. That is your coefficient of determination. It just tells you how accurate your line of best fit is, how closely it matches the data. And if you turned that on previously, it should still be on, which will give you your r squared value here, which shows that it's at 0.992. So in other words, it matches the data by 99%, which is pretty accurate. Okay, that question's done. Then it says graph the equation using your calculator for this. That tells you your domain, where your x values should be, so we can change our window right away. The lowest your x should be is 0, the highest will be is 80. So now we can go and graph it. If you did that extra step, when you go into your y equals, you should see that that equation is already stored into your calculator, so you don't need to round. Once you round, you lose accuracy, so we like to keep it exact if we can. Okay, so it says we want to graph it, and it told me my x values are between 0 and 80, so I'm going to go to my window. My minimum is going to be 0, my max is going to be 80. I'm going to change my scale to 10, that's just how many notches are going along your axis, just so it's not too jammed. And looking at my y values in my chart, the highest it goes to is 7.2, so my y max at 10 looks pretty reasonable to me. Now I'm going to graph it, and you can see it makes a nice logarithmic curve. Now we can move on to part C in our question, where it says graphically determine the thickness of the ice 49 days after freezing. So what that's telling me is I want to know how thick the ice is after 49 days. It's telling me that my x is 49, and I want to know what my thickness is. So again, just like last time, if you know your x value, you can go into your calculator, go into second calc, and you can go into value and enter in the x value that you have, and hit enter. Now it tells you what your thickness is here. Your y value will be your thickness, which gives me 6.826 when I round it. Don't forget your units. It's a silly thing that's easy to forget, but makes your answer more accurate if you include your units, so we know what you're talking about. Now it says use your calculator to determine to the nearest day the number of days below freezing necessary for the ice to reach a thickness of 6.8 inches. That's a typo. Round to the nearest tenth. So now it's telling me my y value, my thickness, is 6.8. And I want to know what my x is, the number of days. So when you have your y value but not your x, this one's a little bit trickier. You have to find your point of intersection. So under your y2, you're going to enter 6.8 in your calculator. You're going to look at your graph, and wherever they intersect is where those two are equal. So now we're going to go to calc intersect, the fifth one down. First curve just hit enter, second curve hit enter, and then move it to where they intersect and find that point of intersection. So here's my point of intersection. I'm going to write that down, and your x value is the one that you're looking for, your solution. We're looking for x. So point of intersection, that's an I. 48.563, 6.8, and your x value will be your solution. They said round to the nearest tenth, and it's days. So after 48.6 days of temperatures below zero, your ice should be approximately 6.8 inches. I'm not going to go through example 2. You can try that one on your own if you like and make sure your values match, then you know you're doing it correctly. I will briefly talk about example 3 though. So everything I'm doing is on calculator so far, but you can do it algebraically as well, doing the work in a different way rather than using that graphing function on your calculator. I'll show you briefly that just in case it's asked, but when you do it algebraically, you end up using rounded values, so it's going to be slightly off, not as accurate as when you use the graphing function. So same thing here, it's a sample of bacteria taken from a patient, so it shows after 5 observations how much the bacterial population was. To determine the equation, I don't think I'm going to go through the whole calculator steps again, but you're going to enter this into list 1. This into list 2, and you're going to go down, and in this case, be careful. We're combining exponential and logarithms in this regression worksheet, so make sure you read carefully. This time I'm wanting you to determine the equation of the exponential function. So when you go down your list, you're going to use your EXP regression instead of your LN regression. When you do that, in your calculator, entering that into your list and doing the regression, you should get that as your equation. And again, ask me if you're stuck on anything. Once you have that, instead of storing it in my calculator, because I'm going to do it algebraically, again, storing it in your calculator gives you more accurate way, so that's the way I generally go with. But let's say you have a written response question or something. Sometime you want to do it quickly by hand. It says, if this growth rate continues, determine algebraically how many bacteria will there be when the lab technician makes the 10th observation. So essentially it's telling you that your x is 10. So you can do this algebraically. All you have to do is take your equation and now replace the x with a 10. Most of your questions are using a calculator and the graphing function. Like I said, it's more accurate, but if you wanted to do it algebraically, then all you have to do is type this straight into your calculator and you can get your answer. So we would have 4,120.076, 1.500 to the exponent 10. And then it'll tell you how many bacteria approximately. If you did it on your calculator, you'll see the answer might be higher or lower than that on your calculator, because here we've done the rounded version instead of the exact stored version. So that was approximately 237,584 bacteria. We can do the same thing here as well. It says, after how many observations would we see approximately 70,395 bacteria? It says solve algebraically, that means I want to see your work for it. That's telling me my y value is 70,395, and I want to solve for x. So we're going to use our equation, and instead of y, I'm going to replace it with 70,395. And now I have to solve it algebraically, so don't forget you can still do this, right? First thing you're going to do is divide both sides by 4,120. To get this on its own. 1.500, I can just write it as a 1.5. At this point, the zeros don't mean much. Now it's an exponential equation. I'm trying to figure out what x is the exponent. So let's take the log of both sides. Let's trace this here. So if I take the log of both sides, in order to figure out what that x is. And remember, once you have the log, you can pop that exponent in the front with your logicals. And now you can solve for x. I'm just going to divide both sides by log 1.5. Running out of room, but we'll give it a whirl. Oops. And I wrote that wrong already. So there's my first log, and I'm going to divide both sides by log 1.5 to isolate my x, and then you just have to be really careful typing this in. So I'm going to type it in and show you, and we should get 7 observations. So you should see it's about approximately 7. Okay, so typing this one in. First of all, I have this, the log of this whole expression, 70,395 divided by 4,120.076. And then this whole thing's going to be divided by log 1.5. And you can see at approximately 7 observations, very, very close to the number of 7 observations is going to be your answer. And that's it for today. And that's it for this unit. So we will be starting our next unit very briefly. Have a great day.